want to get those definitions out of the way so we can hit the ground running here. Some of this should be review. Obviously, we've had these before. It's not the first time that we've talked about these things. Okay. All right. Let's talk about factors. Okay, when we talk about factors, we want the numbers that you multiply together to get a certain product. Okay, for example, factors of 32. Factors of 32 are 1, 2, 4, 8, 16, 32. Those are the factors of 32. How many factors are there? How many? 6. So there's 6 factors. Would that be more than 2 or exactly 2? More. So therefore, this is a composite number. Okay, because it has more than 2 factors. All right, prime numbers have exactly 2 factors. Composite numbers have more than 2 factors. Okay, if we list the factors of, let's see here, 64. Okay, one of the ways I've started doing it with some of the 6th and 7th graders is we do this. We draw us a little T, put 64 on top. Then on the left side we put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we go, okay, 1 times 64, 2 times 32. Does 3 go into it? No, so we mark it out. Does 4 go into it? Yeah, 4 goes into it 16 times. 5 doesn't go into it, so we mark it out. Does 6 go into it? Yeah, 6 times 9 is 64. So now 7 doesn't go into it. 8 times 8 equals 64. Okay, so 9 and 10 I don't need down there, so now I just start listing them. I start right here, and I work myself around back up to here. So that's 1, 2, 4, 6, 8, 9, 16, 32, 64. Okay, that way I don't leave any of them out. Okay, so that's what we've sort of started doing in the younger grades to try to help us with factors, because I know usually we'll miss a factor, or we won't list them in their pairs, and then we'll miss one there, and so it's an easy way to try to get all of them down. All right, so those are factors. Okay, in other words, what we're saying, 1 times 64 is equal to 64. 2 times 32 is equal to 64. Okay, 4 times 16 is equal to 64. 6 times 9 is equal to 64. 8 times 8 is equal to 64. So these are all factors. Okay, it is factor times a factor equals a product. Okay, so that's factors, finding the factors of a number. That would also tell us that this number is also, composite. Because why? It has more than 2 factors. Okay, so those are factors. So as we're looking at numbers just to tell whether they're prime or composite, what's 9? Is it prime or composite? Composite. What's the factors of 9? 1, 3, and 9. Okay? So it would be composite. How about 51? Well, since I've been talking to you about this number since the 6th grade, it is composite. Okay, let's remember our rule. The rule says that if for 3 to go into a number, you add up the digits. So if we say 5 plus 1, 5 plus 1 would be what? Okay, does 3 go into 6? Okay, 3 goes into 6, so 3 will go into 51. Okay, and it goes in there, 3 goes into it 17 times. Factors of 51 are 1, 3, 17, and 51. Okay, so it is composite. And I've been telling you that number is going to show up on tests, and it has been since y'all were in 6th grade. All right, now, what about 23? It is prime. Okay. Remember, the first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and so on. Okay, remember, there's only one even number that is prime, and that is what? 2. That's the only even number that is prime. Why wouldn't 4 be prime? Because 2 can go into it. Okay, same thing with 6, same thing with 8, same thing with 10, so on and so forth. Okay, so then let's look at prime factorization. Okay, prime factorization. You have factor tree, and you have inverted division. Okay, remember that prime factorization is writing a number such as 120. Prime factorization is taking the number 120 and writing it as a product, a multiplication problem of its prime factors. Okay? Now, factor tree, we do what? To prime factor 120 with the factor tree, what am I going to do? A common factor with 120? No. Huh? 6 times 2 is 12. Okay, so why would I do 6 times 2? Right, you have to have 2 factors. That's why it's called the factor tree, because you're coming up with 2 factors. When they multiply together, they equal 120. So, that's not anywhere what you were saying. 12 and 10. Okay, once again, you could use 6 and 20. Okay, those are 2 factors that equal 120. 12 and 10, like we've done, doesn't matter. You'll still end up with the same prime factorization. So I keep going until I hit prime numbers. Over here, I have to factor 10. I come up with factors of 10 is 2 and 5. So those are both prime. So my prime factorization is 2 to the third times 3 times 5. Okay, now 2 to the third times 3 times 5 must equal 120. If it doesn't, then you've done something wrong. Okay, that's factor tree. Now, inverted division is simply that. You just invert the division bar. And you divide by prime numbers. First prime number is 2. 2 goes into 120 60 times. 2 goes into 60 30 times. 2 goes into 30 15 times. Does 2 go into 15? No. So I move to the next prime number, which is 3. 3 goes into it 5 times. There is your prime factorization. 2 to the third times 3 times 5. You can do any way you want to do it. Now, depending on which, it doesn't matter which way you use, you see that we both ways, inverted division and factor tree, came up with the exact same answer. They will, providing you do the math right. Okay? So let's look at another example. 154. Okay, the problem you run into with the factor tree is when you get like 154 that's not just obvious what two factors you can use, you get bogged down. And you sit there and you go, okay, two factors of 154. And you're sitting there going, I don't know. Meanwhile, I'm over here doing this, and I'm done. While you're trying to figure out two factors of 154. And then eventually what you do is you do this. That's why, and if you want to do it both ways, for the easy ones, like, let's say 60. Well, 60 is easy to figure two factors, 6 times 10. For the easier ones you think are easy to find factors, do the factor tree. For the harder ones where you're just going to use 2 or something like that, then use inverted division. I don't care. I have one class that pretty much one class of 7th grade that pretty much uses only inverted division, and I have another class of the 7th grade that pretty much uses only factor tree. And it's just the way your mind thinks. There's an easier way if your mind thinks that way. So the prime factorization of this was 2 times 7 times 11. Okay, remember on inverted division, when you get to a prime number at the end, you stop. Well, let's remember, the number 1 is not prime. It is not composite. Do not include it in your prime factorization or it will be wrong. Okay, if you just do this, that is wrong. You have to have the multiplication. The definition of prime factorization is that it is the product of the prime factors of a given number. Product means to multiply. Okay? So I want you to do this one on your own. 210. All right, Vivica, what'd you get? 2 times 3 times 5. Did you do inverted division? Yeah. What's the last number? 5. No, underneath. You have 5, and then you have another number underneath, don't you? No, I do. What do you have? 2 times 3 times 5 times 7. Yeah. Now, it looks like this. 2 be 105. 3, or you could actually use 5 here. Be 21, 3, 7. You got to include that 7 there. If you didn't get to the 7, then you didn't take it far enough. If you took it just to the 5, if you did this, 2, 105, 3, that would be 3, carry my 1, 35, and you went 5, you still would have to have a 7 there. Okay, so the actual answer is 2 times 3 times 5 times 7. No. Now, if you did it factor tree, the easiest 2 factors to use for factor tree for me would be 21 and 10. Prime factor 21 into 7 and 3. Prime factor 10 into 2 and 5. Those are all prime. So either way, like I said, you still come up with the same answer. All right, let's talk about the dreaded word monomial. Okay, a monomial, by our definition, is a number or a variable or a product of those things. Okay, so a monomial could be 3, could be A, could be 3A, could be A, B, C, could be 3A squared, could be XY squared. Those are all monomials. Okay? Now, if I'm going to factor monomials, okay, if I'm going to factor monomials, the first one is an easy one. 11 times C times D. That's what I would write. 11 times C times D. That is a monomial factored. Okay, you're just taking them down to their prime factored state. Let's do another one that has this. 21AB. 21AB would be 3 times 7 times A times B. So this one, 35RS to the 5th. Huh? 3 times 7 is 21. Remember from like 2nd grade? Yeah, okay. Wait, so you're basically doing prime factorization to the number and then adding A times B at the end? You're not adding A times B, you're just spreading them out. Like this one here would be this. 5 times 7 times R times S times S times S times S times S. That is your answer. Oh yeah. All right, so that's how you factor monomials. Everybody turn your books to page 175. And let's look at problem number 46. I hate word problems. Hey, word problem. Please don't make me do a word problem. Please don't make me do a word problem. I've got this baby picture strapped to my pajamas, but please don't make me do a word problem. See, now you can go on YouTube tonight and let your dad hear me make fun of you.
Can you not cut that out?
I could, but why would I?
On one of the videos. It's funny when she was in kids something when I'm listening to it, and then she's like, "Wait, how'd you get that?"
All right, number 46. Number 46, 175 is what page we're on. Says the U.S. Mint began issuing state quarters in 1999. There will be one state quarter for each of the 50 states. Here collecting the state quarters and want to design a rectangular display with the same number of quarters in each row. How many ways can you arrange your display? Okay, so they want it in a rectangle. You know, a rectangle could look like that. Rectangle could look like this. But they want to have the same amount of coins in each row. So obviously, what's the first way that should be the easiest way to do that? Huh? Okay, 2 rows of 25. So 2 by 25. Okay, what's another way that we could do it? 5 rows of 10. Thank you for helping her. Hey, what's another one? Huh?
I'm trying to make those pictures. Oh, 2. Oh, she's got some height. Oh! That's it. What about 25? No, 4. Wait, why'd you pause it?
So what's another way?
25 times 4.
Yeah. 1 row of 50. That's it. Isn't it? Except you can go 25 by 2, you can go 10 by 5, and you can go 50 by 1. So how many rows is that? Or how many ways? 1, 2, 3, 4, 5, 6. Okay? So there's 6 different ways that you could have the same amount in each row. They didn't clarify whether they wanted more than 1 row. They didn't clarify if they wanted a certain amount of rows. They just said, how many rows, how many ways can you do it? Okay? All right. Okay, your homework. Your homework is 4.1, 1 through 31. Oh, hang on, that's wrong.
Oh, why don't you just give us 84 problems?
All right, we got 20 through 31, 34 through 56. Okay, 20 through 31, and then 34 through 56. All right, that is due tomorrow.